Good afternoon, everyone. My name is Xiaorui. I'm currently an assistant professor of computer science in North Carolina State University. I graduated from Michigan State University last summer under the supervision of Dr. Jilian Tam. It's my great honor today to share my dissertation with you. And I'm honored to receive this runner-up for the KDD Outstanding Dissertation Award for my dissertation, Efficient and Secure Message Passing for Machine Learning. So today I will give, sorry. Okay, works, sorry for the technical issues. One of the major topics we study in this dissertation is message passing for machine learning. The reason is that, so what is message passing? It basically means the algorithm that in which the nodes in a graph try to do some local computation that depends on the information at this node itself, as well as the neighbors. So you will see, for instance, the node V4 can receive the message from V2, V5, and V6 in this graph. The reason we started message passing is because it's a very, very powerful and fundamental building block for many important machine learning and data mining problems. So two of the major application of message passing we study in this dissertation is the distributed machine learning, where in the training of machine learning models, especially large models, where the communication becomes a bottleneck, the message passing can be dominating. And another perspective is graph neural networks, right? So message passing layer is one of the building block of designing graph neural networks. So we are trying to solve some security concerns, robustness problems related to graph neural networks. Of course, message passing are also a very powerful building block for many other scientific computing problems. So first of all, I would like to give a little bit motivation for message passing in distributed machine learning. Essentially, in a time of big data, we try to utilize or take the advantage of computation resources of many, many machines, for instance, like GPUs, CPUs. And the major goal is to try to optimize some objective function, right, defined for machine learning problems that can be formulated as a finite sum problem. So here's a popular architecture or distributed machine learning system as known as parameter server architecture, where you have this center server and many other work servers, and they kind of coordinate to achieve some computation goals, right, to minimize the training loss. One of the key steps of this training process is trying to communicate the information between the machines to coordinate this learning process. So, but the problem here is when you increase the number of machines and when the machine learning model becomes large size, the communication time can dominate. So in this case, when you further increase the machines to like 30, 64, 100, the training time actually does not reduce. In fact, it's even increased, right? It's very far away from ideal like linear scaling we try to achieve in parallel computing. So the reason is that the communication time actually has a dependency on the network latency as well as the proportional to the model size divided by the network bandwidth. So especially nowadays, as we know, like large language models and many other powerful machine learning models really relies on this kind of scalability, right? We try to increase the number of parameters to say like 175 billion parameters. So in this case, the model size can be extremely large. And for machine learning training problems, we have to train this model by like thousands iterations, much more than that actually. So every single iteration, we need to communicate the model from one machine to the other one for many, many times. So that's why the communication becomes a very important and critical bottleneck for distributed machine learning. So in this dissertation, we actually studied multiple solutions to solve this bottleneck for message passing. One of the strategies is in centralized or the parameter server architecture. We propose this bidirectional communication compression that can reduce the size of the message by, say, 32 times at least, when we communicate the information from the worker side to the server side, and especially for both directions. The other direction we try to work on is the decentralization, where we remove this bottleneck of parameter server. So we propose message passing algorithm on this general graph topology, as long as it's connected. We can design algorithms to support this kind of a general decentralized machine learning system, so that we only need to communicate information between the neighbors. Right, so in this way, we can remove this bottleneck as the parameter server. More than that, we also propose a very innovative algorithm for the communication compression in this decentralized case. So due to the time limitation, I will briefly kind of mention the key problem and challenge we try to solve in this work. So the benefit of decentralization is that, as I mentioned, we don't need to communicate all the information for all the workers to one, like a central server, right? Otherwise, the central server will become the bottleneck. In this case, the bottleneck of this decentralized system only relies on the node with the maximum degree, right? So then we can design a balanced a network with like evenly distributed degree, so that the communication workload for this whole system becomes extremely balanced, right? And can be perfectly parallelized. But the challenge of designing machine learning algorithm for this kind of decentralized, general decentralized algorithm is that there's no global consistency. Like for each single iteration, the model parameters, they are not the same. Then how do we guarantee the convergence, right? So especially this problem of lack of consistency actually hurts the convergence of the algorithm if the data distribution of your loss function defined on each single service, working service, is different, right? Because they are moving to different directions. And then how do we control their conflict and make sure they're converging to the right solution? On the other hand, we try to do the information or message compression in this communication process. The benefit is that we can reduce the communication bit, right? For instance, from 32-bit flow points representation to maybe 1 bit, 2 bit, that can reduce about like 95% of the communication cost. But actually, at that time, there are quite a few decentralized algorithms with compression. But their problem is that even we design compression algorithm, but if you sacrifice the convergence of the algorithm, right? We reduce the time for each single iteration. But it takes much longer to converge. And in a lot of time, it does not support high compression ratio. For instance, they probably can only compress this message from 32 bits to like 16 bits, 8 bits. But even though they are not robust, and they are very sensitive to hyperparameter tuning, and we actually try the algorithm, it's very easily to diverge. It means that it does not converge to the right solution. So one of the open questions we try to solve in this work is that, can we design better algorithm with much better communication efficiency, but we do not sacrifice the convergence property, right? So we actually designed this very dedicated algorithm. It's hard for me to explain this in full details, but the major point is that this is really a dedicated design algorithm that we have several key points. One is to have a direction correction that mitigates the conflict of different sub-objectives. So we can make sure they are actually moving to the same direction once the algorithm converges. And we also have a very novel compression procedure that can reduce the compression error once the algorithm converges. Actually, this compression procedure has been widely applied in many new works tackling similar problem. And one of the main challenges here is we also design an error compensation that can tolerate the error introduced in this compression process, right? So basically, when we send a message to other machines, the information is not accurate. Although it gradually converges to accurate, but when it becomes, before it becomes accurate, how do we reduce the impact of those errors? So it's actually handled by this error composition. It's implicit because the idea is we try to maintain this variable d in a subspace of the Laplacian matrix. So that's why globally it actually does not contain the compression error. Okay. So it turns out to be the first linear convergence decentralized optimization algorithm for this type of problem. We precisely describe the convergence property of this algorithm, and the theory actually tells that this constant C tells the compression error. And it tells us this algorithm converges no matter how aggressive is your compression. However, there's a bound tells us as long as the compression is somehow reasonable, within some range, it actually does not impact the convergence at all. So this is the very surprising result from this work. So we do some numerical analysis about this algorithm. We actually figure out this is the only algorithm that can achieve linear convergence for decentralized optimization, and this can support very aggressive compression, like 1 bit or 2 bit, compared with many other previous works that only support like 8 bit, and it's very robust to hyperparameter tuning. Basically, don't need to tune anything here. It also works well for the deep learning problems, especially for the data heterogeneous problem, where all the existing works does not even converge for this case. So in addition to distributed machine learning, message passing is also a fundamental building block for graph neural networks. I guess most of us should be kind of familiar with message passing in graph neural networks. It's basically try to merge the information in a local neighborhood, right? By this neighbor aggregation. It provides an effective way to kind of take the advantage of both node feature and the graph structure information. But one of the challenges we have been trying to deal with is the security concern. It's very sensitive. I mean, the feature extraction and prediction from graph neural networks is very sensitive to the adversarial perturbations, either in the graph structure or the node features. One of the key reasons is that graph neural networks largely relies on this smoothness assumption, which basically says if two nodes connected, they're likely to be similar in a way, right? But adversarial attacks, as we studied in this paper, actually tells us the major attacking mechanism is trying to connect nodes from different class, and then they can mixture their representations that can destroy the prediction of graph neural networks. And one of the design principle, we try to analyze why this adversarial attack can happen in principle. So one of the reasons is that in most of the time, we try to design neural networks from kind of spectrum graph theory, right? We do this Fourier transform, get a Fourier coefficient, and try to do the, like for instance, polynomial filter on this Fourier domain, and then there's an inverse transform to go back to the original domain. So then, typically this polynomial filter actually transform to a very simple message passing, like xk plus 1 equals 8xk, where A is an adjacent matrix, or some complex combination of this kind of aggregation rules, right? So for instance, with residuals and so on and so forth. So the major problem with message passing design from this perspective is that it tries to allocate some global smoothness, right? You can see this aggregation rules does not distinguish different regions of this huge network, right? So why do we need to believe a whole, like for instance, like social network that has millions of and even billions number of nodes, why they have to share the same smoothness over the whole graph? That's a big problem, right? So for instance, you connect a lot of nodes with different types or different labels in this region, but they're not with this kind of smoothness in another region, right? So that's the key problem of the lack of robustness in graph neural networks. So one of the perspectives we try to advocate over the last few years is not to design the graph neural networks building blocks through the spectrum graph theory. Instead, we can model this smoothness in a much more flexible way. For instance, we define our prior knowledge from an optimization problem, right? So for instance, we can maintain the relation between the representation for one layer to the next layer. And then we can model the smoothness prior by some regularization like this. So actually, this is a typical formulation for, that corresponds to the classic graph neural networks. So this unifying view of designing graph neural networks actually help us to build a connection with a lot of literature in robust signal processing and robust statistics. There are tons of literature that try to deal with robustness problem in data science, right, statistics. So here I want to, due to the time limitation, I want to give you one specific example how this can be dealt with to use to tackle the robustness problem. So as I mentioned, the attacking actually happens in such a case where you have two clusters, right? And within each cluster, their labels or features should be very similar. So we hope the representations for 1, 2, 3, 4 is the same. And the representation for 5, 6, 7, 8, 9, 10 should be the same, right? But the attack tried to make a connection between these two clusters. And then after several times of aggregation, their feature becomes similar and similar, and so that we cannot distinguish their representations or labels, right? So that's, if we can enforce some sort of local smoothness, right? Within this region, it's very smooth. Within this region, it's very smooth. But between these two regions, there should be a transition stage, right? So that should not be smooth within this transition stage. So one of the methods in non-parametric regression called trend filtering provides exactly this motivation to model this kind of piecewise polynomial signal in graph signal. For instance, there's a total variation penalty described by the difference operator. So we can model the signal like a piecewise shape, depending on the order of the difference operator. So motivated by this kind of very classic non-parametric regression approach, we can actually design a proper local smoothness prior for graph neural networks. And of course, we need to design efficient optimization solver that gives us the message passing scheme. One of the example looks like this. It's a little bit complicated, but it's very general and covers many existing message passing graph neural networks as special case, and even covers the very popular medium estimator as a special case. So through the numerical study, we actually figured out, we call this model elastic GNNs. It's very robust to the adversarial attack while maintaining very good clean accuracy. Right, compared with many works that kind of sacrifice the clean accuracy to achieve better robustness. It's achieved both. Okay, so that's the end of my presentation. Finally, I would like to express my deep thanks to my synthesis committee collaborators, lab mates, advisors, and the award committee to your support and encouragement. I'm open to any questions. Thanks.